All right. So hello, my name is Luca Silveri. I just started my PhD at the Low Gravity Science and Technology Lab at Georgia Tech. And today I'll be presenting the paper that was published at the AIWA SciTech 2026 forum titled Analysis of Low Gravity Sloshing in a Spherical Tank. So let's start with some motivation and background. What is sloshing? Sloshing is the dynamic behavior of liquids in moving containers, and it was first recognized as a problem for space in the 1950s following the loss of the second Jupiter C launcher. Sloshing can be a problem for space because it can induce torques and forces on the tank that affect attitude and dynamics of launchers and spacecraft. We can see two examples here on the right. The Near Shoemaker spacecraft by NASA that missed the critical burn for meetup with the asteroid Eros, and this was caused by sloshing and generated a delay in the mission of almost a year. And the second example is the Apollo 11 lunar module, which had to perform a last-minute correction maneuver, missing the original landing spot. And one of the plausible causes for this was sloshing. Other potential problems that can be caused by sloshing are gas injection into engines and liquid propellant into venting system. And since future developments in space exploration involve larger tanks and long coast phases, sloshing has to be addressed. So how is sloshing modeled today? Well, sloshing is addressed in design and mostly in flight for guidance, navigation, and control algorithms, which act in real time. Real-time action and coupling the equations of motion between the flexible structures of the spacecraft and the fluid propellant in the tanks require reduced order models. While we have mature models for high gravity sloshing that have been extensively verified with experimental data, this is not the case for low gravity. In low gravity, we have a lack of experimental validation. So the high gravity sloshing models have been adapted to low gravity. One of the most common ones is the pendulum analogy. And today, simplified pendulum analogies are widely used to model low gravity sloshing. And we can see some examples in the simplified pendulum analogies have been used in the Cassini GNC algorithm, in the Emirates Mars mission GNC algorithm, and in the Europa Clipper GNC algorithm. But they have also been adopted for solar panels slosh coupling analysis, stability criteria and resonant motion for sloshing in spinning spacecraft, attitude maneuvers on liquid filled spacecraft, attitude acquisition, attitude dynamics, and machine learning for GNC algorithms. So even if pendulum models may be appropriate for high gravity acceleration regimes, the lack of experimental validation casts doubts on their validity in low and microgravity environments. As a result, in 2023, a low-gravity slosh workshop organized by NASA stated, at present, there is not a widely accepted reduced order model that can be used in GNC simulations that will provide an accurate prediction of low-gravity slosh behavior in flight. So in this context, we realized the sloshing imaging and load analysis, SILA experiment, whose goal was to acquire experimental data to test and validate reduced ordered models and CFD simulations for low gravity sloshing in spherical tanks. And this was done with a parabolic flight payload, then the implementation of a CFD setup in ANSYS Fluent, and finally the implementation in MATLAB of the spherical pendulum mechanical analogy. To contextualize the experiment, we can see that since the 1960s, multiple experiments have been performed for sloshing in low gravity, and the SILA payload fits in this history of experiments. But if we consider spherical tanks, so experiments that only were performed for spherical tanks, then we only have an experiment performed in 1970 by Dodge and Garza using the ultra-small technique, and an experiment performed by ESA and CNES on the International Space Station in 2017. So SILA experiment aims to continue this line of experiments. Let's see the methods. So the experimental setup, let's take the laser pointer, is this is the setup of the experiment. there are two cameras which are pointing in orthogonal views, a spherical tank filled at 33% of its volume by water. Then an accelerometer records the acceleration field. The BME 280 records ambient data. And the load cell, which is visible here, and also in this image on the right, a load cell measures the force that the fluid exerts on the tank along one axis. So moving on, the low gravity environment was obtained with the parabolic flight. The video on the left shows a parabolic maneuver of a parabolic flight, and this gives, as can be seen on the right, gives some time of low gravity environment. Then there is a transition in high gravity, and then another around 20 seconds of low gravity time. The acceleration are lower than 0.04 g during the parabolas, with the average close to 0.02 g for many of them. And this puts us in a bond number region between 1 and 100, which is the low gravity environment. The bond number measures the relative magnitude of inertial and capillary forces. So a bond number closer to 1 will characterize a low gravity environment. So let's see the onboard operations. At the start of the flight, the payload is active. When we enter the first parabola, cameras start recording, and LED flashes 4 times for synchronization, and sensor data acquisition starts. During the parabola, we keep recording, and when we exit the low gravity parabola, a 15 seconds timer is triggered, after which videos and data are saved, and data and video acquisition immediately starts again. And when we enter another parabola, nothing is done. The payload keeps acquiring data, and then when the parabola will be left, so when the low gravity period is over, then 15-second timer is triggered, and then all the data are saved in separate files. This is done to safely save data after each parabola, but still be able to acquire data for the transitions between low and high gravity. So this was the experimental setup. The numerical setup has a model, a geometry of an 8 centimeter diameter sphere, which basically reproduces the tank, the experimental tank. The meshing is unstructured polyhedral 3-dimensional. 1.09 million cells are used. Sensitivity analysis was performed first in high G and then in low gravity on the inclined down brake case. Setup is transient with an adaptive time step, and the implicit volume of fluid has been implemented in ANSYS Fluent. On the bottom right, you can see the initial conditions and the boundary conditions. So the stationary wall and nozzle condition are implemented, free surface condition and the continuous surface force, and finally the wall adhesion. The fluids are air and water, and all the parameters have been measured on the experimental setup. For what concerns the analytical model, the spherical pendulum mechanical analogy was implemented. The idea behind mechanical analogies is to replace the liquid with an equivalent mechanical system. The model must match, of course, the natural frequencies of the fluid. So there is a need for masses free to oscillate, and these are the equations of the spherical pendulum that have been implemented in MATLAB. So let's see some results. The SILA payload collected over 27 parabolas video, force, ambient, and acceleration data. Acceleration was recorded only for 17 of the 27 parabolas due to a malfunction. And during these parabolas, low, mid, and large amplitude sloshing are observed. So all 3 types of sloshing, all these 3 types of sloshing. And as we can see here, yes, so by low amplitude sloshing, we mean the oscillation of the free surface around its equilibrium position. By mid amplitude sloshing, we mean both oscillations of the free surface around the equilibrium position, like can be seen now, and also a bit larger movements, the free surface and the contact line. And finally, with large amplitude sloshing. In large amplitude sloshing, we can observe large motions of the contact line on the walls and of the free surface, as can be seen on the right. So let's move on. The free surface and the center of mass have been tracked from the acquired videos. As it is possible to observe on the left, the two cameras provide two orthogonal views of the experiment. From each of these views, the interface is selected manually. Sorry, the free surface is tracked manually, and then the best linear approximation is computed. And then the two best linear approximations that are orthogonal give the best planar approximation of the free surface. And here we can see the comparison between the real video data and the tracked ones, which are the best linear approximation of the free surface. And as it is possible to observe, there is a pretty good matching, and the green dot represents the center of mass position. This is computed analytically, just preserving the volume of the fluid in the sphere. So a first analysis can be performed by carrying out the Fourier transform of the center of mass displacement versus the acceleration field. And as it can be seen here, where the red arrows point, the center of mass position Fourier transform shows some peaks where that are not visible in the acceleration profile. So this shows a fluid response, a clear fluid response that is not caused by external excitation, but is attributable to sloshing. For what concerns the CFD setup, the CFD setup was verified in zero gravity. Here you can see different contact angles as boundary conditions, and in white overlapped on the image is the free surface shape computed analytically. So as you can see, there is a great matching between the CFD and the analytical results. So the CFD setup is validated for the steady state behavior. For what concerns the dynamic behavior of the system, the partial orientation time was chosen as parameter to validate it. And this was computed experimentally by Sigurd, Petros, and Otto. And for our experimental setup, it is around 0.41 seconds. On the right, you can see the partial orientation time computed numerically. So this was computed by tracking the middle point of the free surface. And as you can see in the right video, the partial orientation time is the time that the middle point of the free surface needs to cross for the first time its equilibrium position. So as you can see from this graph, it is around 0.31 seconds. So this is the same order of magnitude as the one suggested by the experiments of Sigurd, Petras, and Otto. So the model is verified even in its dynamic behavior. So we can finally see a comparison between the experimental videos, the experimental data, and the numerical and analytical simulations. So on the left, you are looking at the videos from the parabolic flight. In the middle is the 3D free surface computed by ANSYS Fluent, and on the right, the position of the pendulum in the spherical pendulum analytical model. So as it can be observed in these videos, there is a clear mismatch between the experimental data and the simulated ones. While the real free surface tends to bend while maintaining the contact line pinned to the wall, so causing only minimal center of mass displacement, the simulated, numerically and analytically simulated one moves all around the tank. It can be seen on the right that the pendulum undergoes several complete rotations, spanning the entire allowed space. And the same occurs for the free surface in the numerical simulation. So this mismatch can be seen also from these graphs. They show the X, Y, and Z coordinates of the center of mass. In green, the experimental data, and then in blue and red, the analytical and numerical ones. And the analytical and numerical trends qualitatively match together, but they differ completely from the experimental ones. So this mismatch between the experimental and simulated behaviors is caused by simplified implementation of the contact angle. So we can conclude that for the analyzed low gravity range, the contact angle hysteresis is a fundamental physical factor in fluid motion modeling. The contact angle hysteresis denotes the capability, the property of the fluid, of the contact angle of being able to vary with the contact line remaining still. As you can see on the left, the contact angle, so the angle between the fluid and the walls changes, but the contact line remains in the same point on the wall. And this is sketched also on the right. We have on the x-axis the velocity of the contact line, and on the y-axis the contact angle. And as it is possible to observe, there is a range of values for the contact angle, for which the contact line has velocity equal to 0. So from these analyses, main takeaways are that for the analyzed low gravity range, contact angle hysteresis is a fundamental physical factor in fluid motion modeling, and simplified pendulum mechanical analogies fail to simulate it, thereby invalidating their use in widespread spacecraft GNC algorithms. So there is a need for contact angle hysteresis modeling in both numerical simulations and analytical models. And this concludes our presentation, and I will leave you to some low gravity sloshing with my contact information on the bottom.